today's lecture is going to be on practical transform coding, building on what we have looked into in the last couple lectures, and we're gonna end it with showing a very basic audio compressor. So we are getting hands-on. Cool. Let's start with the recap. So last time we talked about this thumb rule for lossy compression, which is for a given distortion measure, we want to allocate more bits to component with higher variance, right? So that was really one of the key takeaways from last lectures. And we looked into this example of water filling intuition for Gaussian sources. And again, like the intuition, like the maths doesn't exactly work out, like the KKT conditions and everything, but the intuition actually like is used in, it's basically applicable for all sorts of lossy compressors which are out there, practical, right? And so this is like one of the key takeaways in some sense. And so water filling problem was, just recalling the problem, we were compressing two independent Gaussian sources with different variances. And then for particularly squared error distortion, right, this is important again, we saw that the rate distortion function can be given by this guy, right? And we saw some takeaways again that you would want to allocate more bits to the signal with higher variance. And so last time's quiz question was also on just this exact thing with some specific numbers. So we considered a setting with sigma 1 square 1, sigma 2 square 3. And then at d equals to 1.5, we asked what are the optimal values of d1, d2. And I hope like this one's obvious that since 1.5 d is greater than sigma 1 square, that means our d1 would just be sigma 1 square and d2 would be d minus d1 in this case. So the answer is just, the fourth one. Then the second question was at d equals to 2, what is the optimal rate? So at d equals to 2, this is same as you can verify sigma 1 square plus sigma 2 square by 2. So basically you will give distortion of sigma 1 square to the first component, sigma 2 square to the first component, and this would imply the rate for the first stream is 0 and similarly for the second stream is 0, and hence you just need 0 bits per source component, right? So again, this is like, I'm not getting into details because we literally covered this in last class, and this is just putting specific values. Okay, and then this one part was at least interesting for this question, which is which of the following is correct. So for d below the two variances, we saw in class that you want to keep d1 equals to d2. This was a consequence of the optimization problem KKT solution which we got. So first part is correct. Again, the second part now asks for d below the two variances, what about the bit rate? So if you think about it, if d1 is equals to d2, our bit rate is half log sigma square by d for each component. So if d1 is equals to d2, then that would imply my rate 1 is actually less than rate 2, right? Because my sigma 1 is less than sigma 2. So this is something like if you didn't follow last lecture, we are equally distributing the distortion, but you are still giving higher rate to the component with higher variance, right? Even when you are working with lower distortion than both the sigmas. And so this is also correct. Finally, for d between the two variances, we know that at least one of the components will have 0 bit rate. We can't really guarantee the second one, right? Because d is greater than sigma, it's like literally the first part. So third is correct. So this was really the answer. Okay, any questions on the quiz part? Everyone is comfortable with the water filling intuition now? Sorry. Okay, so let's continue then. So after the Gaussian water filling intuition, the next part we started looking into was this transform coding setup. And what we highlighted is like transform coding basically provides two main benefits. One, it allows you to decorrelate X. Why do you want to decorrelate? Because once your sources are decorrelated, you can then use simpler quantization schemes to basically get similar level of rate distortion trade-off, right? So that's good. You want lower complexity. And the second benefit was this idea of energy compaction, which is really you can have more energy in the first few components. Again, tying back to the water filling intuition, you want to have components with very different variances so that you can selectively allocate bits to each of these components, right? And so sort of this is really the intuition that you want to allocate more bits to the components with higher energy, right? And as a reminder, this was our block diagram, right? So you inserted a transformation step between your old lossy pipeline. And then whatever you recover, you run the inverse transform to recover back the original symbols. Okay. And finally, we talked about KLT in particular, like the Karunen-Louf transform. Okay, and we did some maths, we revised the linear algebra part of it, but this is really the main idea, which is, so okay, if you forget everything, do remember this. So KLT is basically an eigenvalue based linear transform. So it's linear, and we saw like how you can compute it. And you can use KLT to basically get decorrelated components of X, right? A transform was this U transpose matrix where U was the matrix of the eigenvectors of your covariance matrix of X. Okay, we worked through this formula by just like basic linear algebra, but in today's class we'll look into one concrete example so that you feel even more comfortable about this idea. Okay, but again, like remember this throughout, right? Like the main idea of doing this transform coding is you transform the data, in this case, to a new basis. So this is a linear transform, basis makes sense, where the components are uncorrelated and have different variances. This is really the key thing which you want from your transform. Okay, so today we'll look into some more examples. We'll introduce you to some more practical transforms, which is these DCT. Finally, we'll look at a very basic audio compressor, which you can build using all the components we have learned so far. Okay, any questions so far in the previous lecture before we get started? Okay, I guess we are good. Okay, so we are going to look into one specific example. So consider you have a source which looks like this, where xn is rho times xn minus 1 plus square root 1 minus rho square, so this is just a constant, and then IID normal 0 comma sigma square. Okay, and your x0 is normal 0 comma sigma square. We'll try to understand the transform coding for this source working with blocks of 2, so just k equals to 2 in our setting. Okay, and okay, this is an example of a Gauss-Markov source, like if you know. It's called Gauss-Markov Gaussian because we are working with like Gaussian really sources. And if you recall, like when Shubham talked about Markovian properties, so this one has Markovian. Your symbol at xn just depends on the past symbol and some added random noise, right? So it has that Markovian property. So what I'm showing here below on the left, like this, is just some samples generated from this source. So what you do is like, you just generate these samples and then you collect every 2 of them, and we are plotting them as this 2D plot. So you can think of this as x0, this is x1. Each time you generate 2 samples and you plot it. Okay, and now you can clearly see that there is some correlation, right? Like the next sample would depend on the previous sample depending on this sort of value of rho, right? So clearly you can, once you know the previous sample, you know decent amount about what the next sample is going to be, essentially. So hopefully we should be able to decorrelate and do something with this source better. Okay, so let's get started. First, let's just work out the distribution of this source, right? So my x0 is normal 0 comma sigma square. And then my xn is just rho xn minus 1 plus 1 minus rho square normal 0 comma sigma square. Okay, so let's just work out few of these components, right? Like what their distribution looks like. So just spelling this formula out. So your x1 would be rho x of 0 plus this Okay. And since our noise, so this is like IID compared to like whatever my previous X is, now you can actually figure out the distribution of X1. So this is just sum of two independent Gaussians, and as a reminder for them, the resulting distribution of addition is just your means get added and your variances get added. Okay. So this is just like, remember your basic Gaussian stuff. So your X1 in this case would just be normal. So my X0 is this, right? Okay. And so my X1 would be, my means would be just addition of this 0 plus this 0. And then my variances would be, so I also have this constant, so it just gets squared up. So rho square plus 1 minus rho square times sigma square. Let me just write it like this. And so your X1 is really just normal 0 comma sigma square. Okay, so now you understand why I had this random square root 1 minus rho square and rho constant, just to make our life simpler for this analysis. Okay. So your X1, again, so writing this clearly. Sorry. Okay. So your X0 is normal 0 comma sigma square. Your X1, again, we worked out as normal 0 comma sigma square. And then it's just an iterative process. You can basically show that your Xn will also be just a normal 0 comma sigma square. Right? So the first point you see is that this process is stationary distribution for each individual symbol. Okay. Everyone with me so far? Okay. So next, what we want to do is we want to apply KLT to this to see if we can decorrelate the samples, right? Like we worked at it, we thought about it. So for that, the first step is we really need to compute the covariance matrix, right? Because we first compute the covariance matrix, then we compute its eigenvectors, and that's how you actually generate the transform, okay? And so, question for you guys. So what is the 2 by 2 covariance matrix sigma for this? And just a reminder, if people have forgotten what covariance matrix looks like, it's just the expectation. It's going to be a 2 by 2 matrix where you are just taking this expectation. And one hint really here is that your process is stationary, right? So I's don't really matter, right? While you guys are working, let me also work it out here. Okay. So first, very quick step is we are calculating the covariance matrix. In this case, we know that means are 0. So let's make our life simpler. Let's not worry about these expected values. All of them are 0. We just worked out the distribution, right? And we know that the process is stationary. So you can just write it, your covariance matrix, as where diagonal terms are just expected value of the same element, x0, x0 transpose, here x1, x1 transpose, and the non-diagonal elements are just x1 with x0. So that's the covariance matrix, right? If this was diagonal, then you would know that there is no covariance between components which are away, and these are really just like IID components. They don't have any correlation. So in this case, like working out the expected value of x0, x0 transpose, we also know that this is a stationary process, right? Like x0 has same distribution as x1, so this is going to be same as this guy. And this we already know, right? Because my x0 is same as x1, and both of them are distributed normal 0 comma sigma square. So this guy is just going to be sigma square. Okay. This is just like plain definition of variance. Didn't do anything fancy. Okay. Similarly, we can compute, like again by symmetry, these two terms are going to be same, right? Now let's compute this though. So now this is not obvious, right? Because x1 depends on x0. So we can't just separate things out and write it. So let's just, but we know what exactly x1 is. We have the exact expression for x1. So just let's spell it out and write it. So remember my x1 was rho times x0 plus square root 1 minus rho square, this normal term. Correct? And then I want expected value of this thing multiplied by x0. Visible here? Yeah, okay. Correct? Okay. So anybody just looking at it wants to shout out the answer? And then I'll work it out also.
Rho times sigma squared.
Okay, one of the students answered rho times sigma square, and that's exactly correct. And it's not that hard to see. If you have seen a lot of Gaussians in your life, if you haven't, just see a few more, and trust me, this is not really hard. So first we'll use the linearity of the expectation, and we'll segregate out the terms. So expectation is a linear operator, so you get expected value of rho times x0 square plus expected value of 1 minus rho square, this normal variable, times x0. Okay. Then this term, the first one is just rho times expected value of x0 square, which is nothing but rho times sigma square. Okay. And the second one, we know that these two terms are IID. And again, it's a very basic property of expectation. Once you have like these IID terms, you can just write it down as expected value of the first term, which is this. I'm just gonna write, this is the constant k times normal 0 comma sigma square, and then expected value of x0. But we know both of them have mean 0. So this term just goes to 0, and your final value just turns out to be rho times sigma square. Okay. So your diagonal terms, I'll just sigma square, and your non-diagonal terms, I'll just rho times sigma square. Okay. So this is just like we are doing step by step. We are going to apply KLT to this process. We are working through the steps for this one specific example. Cool. Everyone with me? So in this case, like I'm just writing it down, like you can collect the sigma square term, doesn't really matter, and you get this one row matrix. Okay. Everyone's with me? So what's the next step now? Once you have the covariance matrix, what are we gonna do next? Anyone? What's the next step for KLT? Okay, so one of the students answered eigenvector decomposition. That's exactly right. We have this matrix sigma. We have to figure out its, remember the KLT step, we have to figure out its eigenvalue decomposition, or this diagonal transform where U is your eigenvector matrix, and lambda was just a diagonal matrix of eigenvalues. Okay, so earlier I thought I'll ask you guys to do, but this is not a linear algebra class, so go home and work this out. It's not very hard to work this out, but do it once, like yourself. So this is just a 2 by 2 matrix. It's not that hard to compute its eigenvalues. You can even use like numerical tools. But basically what you can show that in this case, your eigenvalues turns out to be 1 plus rho times sigma square and 1 minus rho times sigma square. So your eigenvalues somehow came out to be like spreading out the variances from these two in some sense, right? And then you can also work out the corresponding eigenvectors, and the eigenvector corresponding to this first eigenvalue, you can show that it basically is such that it's 1, 1. So, sorry, it's basically putting equal weight to both the components, and the one corresponding to the second one is 1 minus 1. Okay. So now, can somebody tell me what are my transformed components based on this KLT? So we found the matrix U, right, using this thing. So we can figure out, so we found our transform. So now we can get the transform components. Does anybody want to say what the transform components are going to be? Remember, okay, so if you are still scratchy about your linear algebra, so in this case your U matrix will basically look like 1 by root 2. I'm just taking this 1 by root 2 common. 1, 1, which is my eigenvector 1, and 1 minus 1. And if you recall, our transform was U transpose, right? So that I'm just gonna continue here. So that's going to be 1 by root 2, just taking transpose. Right? And then your Y is just T times X. So now you can see what this transform really is doing. What are the two components going to be? Anyone? Yeah, go for it.
The sum and the difference.
Exactly. So your components are going to be some normalized versions of the sums and the difference, right? Because when you, let me just, okay, let's just go to the next one. Can you guys see this? Yeah, okay. So again, just same thing, your transform matrix looks like this, what we worked out in the last slide. And therefore, now your transform components is just T times X. So you just multiply this with the X, and you can show that it looks like this. So if you see, what we did is in this transform components, what is this linear transform at the end of the day doing? You are just basically taking some normalized version, so some constant here, and your first component is just going to be the sum of the two elements in your block, and the second component is just the difference between them. And what basically KLT transform does is that these are now we know that these are decorrelated components, right? Actually, I shouldn't have given that away, but yeah, we'll see that that this results in decorrelated components. So again, this is just I'm repeating stuff from previous slide. Nothing has changed. Same example. We know our transform is this, and now what am I showing is on this left side is the same 2 by 2 plot, just showing samples from this particular Gauss Markov source for some particular value of rho. And so this is x1, this is x2. And what I'm showing on the right is the transform data samples in 2D. Okay, so this is now I'm just plotting y1 and y2 for this one. Okay, and now you can see that maybe not that clear with these scales. So this is like, note that the x range is -4 to 4, y range is also -4 to 4. But basically it does feel like, no, that this has reduced the correlation between these two components. Okay. But we can't say, just looking at this scatter plot, they might still be correlated. So the way to check it is really, now we need to calculate the 2 by 2 covariance matrix of y, right? That's really the idea. That's what we set out to do. So can somebody work out the 2 by 2 covariance matrix for y? Actually, I'm going to give the answer and I'm going to leave this as a to do. So why don't you guys work this out at home? It's exactly and if you have any, if you are not able to work out, get us in the office hour or on Ed. But what you can basically show is that the 2 by 2 covariance matrix, so I'm just calling sigma y now, of y will look something like this. Okay, so now the diagonal term for this matrix contains 1 plus rho and 1 minus rho sigma square, and the non-diagonal components are all 0. So, and what I'm showing here is again the same plot. So this is, let me just write it down maybe. This is x1 or whatever, x2, x1. And similarly, this is y1, y2. And what I really changed in this plot was the scale. So now I am not really plotting it with the same scale. So my y-axis goes from minus 0.4 to 0.4. My x-axis goes from minus 4 to 4. Right? So now you can clearly see what this transform did. It sort of resulted in a points which are in a circle, which basically you can't really tell looking at y1 what my next value of y2 is going to be. And another thing it did was it actually spread it out on different scales, right? So it's, if you're familiar with linear algebra, or actually you can just look at these terms, right? Your variance in the y1 is just going to be, so let me just write it maybe. Your variance in y1 is just going to be 1 plus rho sigma square. Similarly, your variance in y2 is going to be 1 minus rho sigma square. Okay. So actually this transform did both the things which we wanted a transform coding to sort of do, right? So the first part was to decorrelate. It indeed decorrelated transform components. And moreover, it also gave us two components which have very different variance. And if we again tap back to our water filling intuition from Gaussian sources, this means I can be very selective about how I allocate bits or distortion to these two components. Right? So basically what we did is for this particular source, we went from the beginning to the end showing like what is KLT doing, and it is indeed achieving the properties we wanted a transform coder to achieve. Okay, I'm gonna pause here for a few seconds to see if anyone has any questions on this particular example. Okay, so everyone with me, they can understand like what KLT is doing, how it's achieving what we set out for it to achieve. Yeah. So now let's discuss like I would say the main idea, not main idea, like the main design choices you sort of get in the transform coding, right? So again, summarizing what we really did was you had some source. So here, okay, actually, it's like you had some source symbol, okay? Now I'm writing it instead of x1, x2. So instead of writing it as x1, x2, xn like we have been writing, just so that it makes sense with our previous example, I'm writing our source symbols as x11, x12, sort of to indicate like the two components which we were working with. Similarly, x21, x22, so on and so forth. Okay, so you have like 2n components here. Okay. So what we did, first of all, in this particular example, we chose that we are going to work with a 2x2 transform, right? So that was a design choice. We decided that so in this particular case, it was obvious that we are going to choose the 2x2 transform because we were working with a very specific Gauss-Markov process where we knew the dependence only goes one sequence step behind. But in practice, you don't really know like how much behind the sort of correlation between these time series goes, or like whatever symbols you are getting goes. Okay. So your first sort of thing is you decide like how many blocks, what's the block size on which you are going to do your transform coding at. Okay. So in this example, we took each two symbol and we transformed it into some y11, y12, right? So what were we doing? We chose like one particular point here. And we transformed it into some other point here, right? So we did a 2x2 and we did it for like many different points. I'm making this up. I don't know if this goes in the right direction. These are just random cartoons, right? Okay. But really like we decided to do this 2 by 2 transform. We could have done 4 by 4, 8 by 8, 16 by 16, really up to us. Okay. But so far we have only done transform, right? This just gives us this transform. But if you recall, like after the transform is the original old pipeline which Tsachy talked about in theory, where you encode, you recall all the old lectures, first 2 lectures on lossy, where we did like quantization, we came up with the code books. You actually have to still do all that. At the end of the day, you have to transmit a bit stream, right? So after you converted it into these transform components, you still need to quantize and send it, right? And the way people do this really, or like if you look at the Gaussian water filling example, like the intuition we got, is you can think of like each transform component as a stream. So like this purple block is like a single stream, and then so in this particular case, since we were working with 2 components, we have 2 streams, okay? And then for each stream now, we can independently apply whatever quantization scheme we want. Scalar quantization, vector quantization. We can again have different block sizes for the vector quantization. Okay. So really, another thing which I want to highlight through this example, and this is like a very common transform coding lossy pipeline, which is first you transform, sort of like this transform to blocks. That gives you the transform components. But then you independently quantize each stream. Why do you want to independently quantize each stream? That's where you actually take the advantage that, oh, both my streams have very different variances, right? Like for example, in our previous case, stream 1 variance. So I'll just write it like variance of stream 1 components is going to be this 1 plus rho sigma square. Similarly, your variance of stream 2 components is going to be 1 minus rho sigma square. So now I can use my water filling intuition to allocate different number of bits to both of these, right? Everyone comfortable with the idea? Okay. So in practice, that basically means now you immediately have 2 knobs to play with whenever you are given some lossy compressor which is working in transform domain. So maybe it's very easy to see it through some example. Let's say you were given 2 bits per sample. And somebody says, oh, go do a lossy compression on top of it. Okay. So first design decision which you have to take really is, what's my per channel or per transform component bitrate split? Right? So this is the idea where we give more bitrate to the component with higher NLG. So what are my options? Okay, maybe I could have given 1 bit to stream 1, 1 bit to stream 2. Maybe I could have given 2 bit to stream 1, 0 bit to stream 2. I just say I'm never gonna transmit this. Because again, you can think of water filling. Maybe I don't need to transmit this. Or maybe like any such split between the 2. Right? It's a valid split. Okay. And then, so maybe let's just write it down. See some confused spaces. So how many bits to allocate to each bit stream? So again, in our previous example where we want to encode with 1 bit per symbol, let's say I decide that I'm going to do 1, 1, which is equal bit split. Or maybe I'm going to do 2, 0. Okay. This makes sense, right? I'm just averaging. So on average, in the 2, 0 case, I'm still using 1 bit per symbol, like the basic idea of block. And then my step 2 is, after I decide this, I can choose quantization for each stream independently. Okay. So let's say I decided with, let's say 1, 1. Okay. So then I can decide, okay, my component 1 or stream 1. So I'm going to be using these terms interchangeably. People in practice also use them interchangeably. So if you're confused, just ask. Sometimes it's called per channel, per component, per stream, depending on the context. So, but I hope you are able to follow what's really going on. If you're not, just ask me. Okay. So maybe I decide for component 1, I'm going to use a scalar quantizer. And I'm gonna keep my, so as soon as I say scalar quantizer, and I know it's 1 bits per sample, I know my codebook size is 2. Right? So this is now going back to our quantization lecture. Maybe for component 2 though, so okay, actually I won't do that. I'll show you exact example. This is just to give you what all options you have. For the component 2, I can say no, I'm gonna do vector quantizer. Okay, and then your problem in some sense, it's like a recursion. It just goes back to what we saw during quantization, right? So now you can think of this second stream as just independent symbols, and you can blocks out of it, and you can create your vector codebook from it. And you can actually compress it in that fashion. Say vector quantizer, that's not sufficient. I also need to tell you what's the sizes of my vectors which I'm gonna work with, right? Let's say I say 2. So I'm gonna work with vectors of dimension 2. So in this case, my codebook size for second component, let me also add a subscript, maybe 1 for component 1. And component 2 is just going to be 2 raised to 2. So it's we are gonna have 4 components, okay? So really, in practice, now you have got 2 knobs to play, right? As soon as you do transform coding. First is you can decide like, okay, what kind of transform we want to do, but after that you can decide at what block size do I have to do this transform. Again, and this is very important because in practice you don't really know the covariance matrix, right? Like you don't know what's really the correlation between the signals which you are gonna get. And then the second knob is the same knob, which is like quantization, right? Like which we have looked at. I can change the number of codebook vectors, I can do vector quantization, I can do 10 other things. Okay. And this you will see in like all practical compressors, like you can play with these 2 things. We'll see an example of it, some version of example of it when we get to the audio coding part, but always remember like, so when you are tuning for RD, you can change your rate distortion based on both of this. And what people do in practice is actually they change both of these and they get these numbers and then they choose the best one for a given rate. So for example, if, again, we'll talk more about it with one specific example, but let's say you're a streaming service. In that case, what you're gonna do, you're gonna actually play with both of these knobs. You're gonna get lots of different compressed streams at different rates, and then you're gonna choose the best one. Sometimes changing quantization is gonna help you more, sometimes changing the block size of your transform maybe is gonna help you more, so on and so forth. Yeah.
In the example of, each stream we give it 1 bit per sample, wouldn't it still end up being a combined 1 bit per sample since we're encoding 2 samples between the 2 streams?
No, so after this step, okay, maybe, can you repeat your question, but I don't know if that was it. So one thing is like after transform, you're gonna do independent compression of each stream, right? So now that has happened. So think of it in this particular example, that's like saying after I have gotten this, I'm gonna lose the 2D structure. I'm just gonna take the y1 values and y2 values, and I'm just gonna compress the y1 values all together and y2 values all together. Was that the question? You still look confused.
Just like for the total bit rate you're given, like you said, you were given a bit rate of 2 bits per sample.
Yeah.
Then when we're allocating it to the streams, isn't each stream?
So actually, I said like 1 bit per symbol. Yeah. So if it's 1 bit per symbol, I can give each stream 1 1, or I can give one stream 2 and the other stream 0. So on average, so everything we are working is on average is an expectation and. Oh, okay. Sorry, maybe. Yeah, my bad. Thank you. Yeah. Thanks. That's a good catch. So I meant 1 bit per sample, really, or symbol. Yeah. Thank you. It's a good catch. Okay. Everyone with me? Any questions on this one? People feel comfortable with the idea that now you have 2 knobs to play with? Okay. So we went ahead and implemented these functions for you. So this is a notebook. Let's see. Okay. Don't want to release notes. It's visible. Nice. Okay. So you can go play with this notebook at home, but what we did was in this notebook, again, for this particular example, we went ahead and coded the whole thing end to end. So we wanted to play with all these knobs. So we went ahead and implemented. Okay. So first we implemented some linear transform because our KLT is basically a linear transform. You have to define some vector quantizer because you need a quantizer at the end of the day after you get these streams to actually do lossy compression. And finally, we also did this transform VQ encoder and decoder, which first transforms the data using a linear layer and then vector quantizes each component separately. Okay, so I'm not going to go into this code because it's not really pedagogical in the sense that if I explain it, it won't really make sense. But I highly encourage you guys to go home and look at this code and see if you understand this flow end to end. So this literally implements the whole process which we discussed end to end for the example. So for example, in transform VQ encoder, you can see that there is a loop over each coefficient ID. So that's like going over each stream independently. And then for that stream, you'll do some vector encoder, a VQ encoder, right? Scalar, you can think of it as a special case of vector quantizer. And so you would vector quantize these symbols, and that will actually finally give you some bit array, coded bit array. And then you also have to basically tell the length. Otherwise, like if you have 2 streams, if you don't tell the length, and you can't concatenate this, you don't really know when the second stream is starting, right? So that's like the similar idea. We have looked at it before in various different settings, right? So you also might want to encode the length of each stream so that you know when the second stream is starting. You can decode it accordingly. And then your decoder does the exact opposite. So again, it basically goes in the inverse loop where it decodes each transform component. So again, you have a for loop. And then within each component, it does this VQ decoding. Yeah. And actually, the implementation of VQ encoder and decoder is also it's very simple, but I would again say, like, if you haven't done it, go do it. It will give you a very good understanding of what's really happening, right? I would even say, like, you can take this as a understanding homework problem. Don't look at this code, try to implement this, come back, see if it makes sense. Okay. But in any case, so we went ahead, and so this is the source we were looking at. And we did some experiments on this source in the spirit of this class. Like, okay, let's actually play with these knobs and see what we get. Again, you can regenerate the results from the notebook, but let's come back. Okay, and so let's discuss the performance of what we looked at. Okay, so what I'm showing here is, first of all, my rho is now 0.9. Okay, so this value is 0.9. The higher this value is, the more correlated your initial components are. Okay. Okay. So the first row just shows a vector quantization experiment. So we are not doing any transform. I'm fixing the bits per symbol as 1. So in all of these experiments, it's the same idea from what we just discussed. So my bits per symbol is 1. Okay. So the first knob which I can play with is the block size, right? So this is just doing vector quantization, increasing block size. All of these experiments are at a fixed rate. Okay. So this makes sense, right? And so obviously as you increase the block size, your distortion decreases. Not surprising. but your complexity also increases, right? So now you have to generate code book in 4 dimensions. You have to figure out points in 4 dimensions. What the second block is showing is a transform coding vector quantization experiment. So TC is for transform coding. So first you transform, and this is using the exact same transform which we just derived for this example, okay? And now after you have decided that, so in all of these examples, I'm fixing the block size of the transform. It's just 2. Again, bits per symbol is always 1. And then I can decide my bitrate split between components, right? Like exactly what we discussed. So I can give equal bit rates to each of them. I can give maybe more bit rate to the second one, or maybe more bit rate to the first one. 0 just means I throw away that component entirely. I don't even care. And so what do you guys think looking at? So this is the, again, all of them have rate 1. This is the distortion. What do you think happened here? So I would say, like, look at this number. So this was 0.163. We are fixing block size 2. Everywhere we are fixing block size 2. Each of the step for the transform coding. And 0.163. And for different bitrate splits, I see very different levels of distortion, right? So what's happening? Not a trick question, just say it out loud.
First component has a lot more variance, so if we dedicate more bits to it, we get lower distortion. If we put our bits in the second, then it goes really high, as we see in the second one.
Exactly. So this is now a very concrete example of what we have been discussing, right? So what we see is, if I give more bitrate to the first component, which had higher variance, remember, like it had 1 plus rho sigma square, right? Variance, whereas the second one had 1 minus rho. In that case, I get something which has much better performance than this 0.163 with equal complexity, right? I'm still, so obviously, okay, not really equal because I have to do the transform step extra, but equal quantization complexity. Whereas if I did exact opposite, if I gave more bits to the symbol which had lower energy, like stream which had lower energy, I suddenly pay a huge penalty. And clearly equally splitting bits between them is not the optimal thing to do. Okay? Everyone's with me? Okay. So now in the next one, I'm going to change the row. And the question really is, what do you expect? If I increase the row, do you expect to see more benefits or less benefits? Okay, more. Let's have a show of hands. Like we can vote this out. This is a binary choice. So I'm going to increase row. So I'm going to increase the correlation. And the question which I am asking is, what do you expect, like the transform coding VQ when I give unequal bitrate splits to the 2 components? Do you expect more advantages or less? How many of you say less? How many of you say more? Okay, at least half of the class is neither more or less, so equal, I guess. Okay, do expect more, right? Because the more correlated the sources are, so there are 2 things. One, it's harder to get good performance from them by using lower dimensional vector quantizer, right? But the main point is, as you change your row, remember the variances were 1 plus rho sigma square and 1 minus rho sigma square, right? So as rho increases, my gap sort of increases, right? So that's sort of allowing me to do more of this water filling stuff, right? Like I want to have more and more gaps so that I can just throw away the lower variance component sooner rather than later. Correct? And so here what I'm showing is the same experiment 99. And now here you can see that, okay, this is 0.107, but Now when I do bit rate split between 2, 0, my distortion just goes down to just 0.03 compared to 0.107 here, whereas here it just barely beat it, right? 0.163 to 0.122. And also, like, you can see how high this gap really is. Like if you allocate more bits to the component with higher variance versus lower variance, or higher energy versus lower energy. Okay, one point I didn't say, but you can see that even in this, like, okay, going to block size 4 still beats this. So again, like so the point really is vector quantization, you shouldn't forget about it. It is really powerful. It's very compute intensive. So you have to be selective about when to throw sort of rocket at your problem versus when you can just get away with an arrow, right? So what transform coding is allowing you to do is at times letting you get away with an arrow, really. And so this is like same experiment, but this time I reduce rho to 0.5. And actually in this case, even while giving the maximum bitrate split, I'm not able to beat it. And actually this I'm going to leave as a take home, think about it, ask in office hour or on ed. But it's actually not surprising that 2.0 is not beating. And I'll give you a hint. So question really is, why transform coding doesn't beat? So I'm not filling in the variables, but you know the variables. Doesn't beat VQ for rho equals to 0.5. And I'll give you a hint. Our gap, our sigma 1 is 1 plus rho sigma square, and our sigma 2 is 1 minus rho sigma square. And at this point, these are Gaussian IIDs, right? You actually know exactly the solution to this problem. So given a total distortion and a total rate, we have worked out the exact solution to this problem. And so when rho is decreasing, basically you are probably in a scenario where variance is not in the middle of the two variances. Maybe the total distortion which is there is below the first component also. So you can't throw away the first component completely. So again, this is like repeat of water filling, right? So remember, in the water filling case, like, we don't always throw away the component with lower variance, right? There is a case when your distortion is lower than the 2 sigma, you still want to keep, but you will give it a lower rate. So in this experiment, I didn't find the correct split. That's really the intuition. You could have worked out the exact bitrate split, and then that could have beaten the thing. Like, go home, think more about it. Actually try to work this out exactly like the previous question, and that will give you some intuition. Any question? Cool, everyone's with me? So I hope this example kind of gave you a better idea of what's really happening with the transform coding. But now let's get into the practical aspect of it. Nobody actually uses KLT in practice, even though we did all this. And we talked about it a little bit, but now I hope working through this example gave you a better intuition why we don't do it. So your KLT is basically dependent on the statistics of input, right? Like, recall we had to, where is it? Yeah. Recall what all we did for this example. We first had to figure out like a distribution given the samples, ideally, right? Or we could have tried to estimate the covariance matrix directly, which is a function of the input data. What that means is, like, I have to recompute this every time I get a new input data, right? I have to keep redoing this computation. And moreover, this computation is not trivial, like, in the sense that it costs you to do the eigenvalue decomposition. Like, we didn't really talk about the complexity aspect of it here, but it costs you some compute time to do all of this, right? So it's not really ideal. You don't want to add an extra compute time at each step of doing the transform. And that's really like one of the main issues with the KLT, right? Another issue which I think one student pointed out last class is, in practice, we don't even know sigma. So we have to estimate it, and there'll be some errors also because of that. Though I think that's still, I would say, the secondary concern. The primary concern really is it's computationally intensive and slow. Yeah, so we can't really work this out. And so this leads us to the practical transforms. And the question really is, I don't want to keep recomputing my matrix again and again, my matrix T for new data. So can I come up with some structured transform, which is a way of saying, can I come up with a fixed matrix, so as to say T, which doesn't change with the data, which is easy to compute, right? And basically has good energy compaction properties. So if your matrix T doesn't decorrelate, doesn't do energy compaction, then that's basically a useless transform. You won't be able to exploit it for the compression part, which we saw later, right? Again, so in the previous example, if you recall, one intuition is, as my correlation increased, I basically got two components with a bigger gap in their variance. And that allowed me to compress my source really better, right? So ideally, I want this energy compaction thing to happen for my underlying compressor, for my underlying quantizer to take benefit. And so we are going to talk about something called DCT, discrete cosine transform, a little bit. And it's amazing, like it's basically used in so many compressors out there. And if you are familiar with Fourier transforms, discrete Fourier transforms and alike, you can think of it as a sibling of DFT. Basically, it's another one of the frequency transform. And this is really, really funny. So Kedar, I think, found out this. This was, was really nice. So he's the author who came up with the DCT transform idea. And you can look at this article. It's actually very fun read, like weekend fun read. And so these are like two excerpts from that article. And so if you look at the first one, what Nasser says is like, what intrigued him was the KLT was indeed the optimal transform, right? So we know KLT is optimal. And yet there is no efficient algorithm available to compute it, right? So that's really the issue. So this guy said the same thing. And then as such, the focus of his research was to determine whether it would be possible to come up with a good approximation to the KLT, which can be computed efficiently, which is essentially what we want to do. And he came up with this idea of DCT, which is used everywhere. So clearly he was very successful in his endeavor. And then even more funny, and this is like an anecdote to research. So if you are doing your PhD or research, don't get demotivated if you believe in your idea, but nobody else does. Because much to his disappointment, in his case, NSF didn't even fund their proposal. So like, and again, like DCT, basically, as Shubham said, like whenever you are opening some image or some gzipping, when you open any compressed file on your computer, at least multimedia files, most likely you are running some DCT transform on that every click. Every time you have an image loading on your browser, there is a decompression step happening, and DCT is somewhere most likely involved in that step, whatever multimedia it is, be it audio, video, YouTube, Netflix, Spotify, it's everywhere, right? So it has clearly made quite an impact. And so after this fun detour, let's get back to this question of the practical transforms, right? Like, so we want to come up with the structured transform. 1 second. Okay. And in practice, there are like, you will see a lot of options for these transforms. So I just said discrete cosine transform is just one of them, but you can think of discrete. So if you have done signal processing in your life at any point, you would have heard some of these terms, discrete Fourier transform, wavelet, so on and so forth. Actually, there's a very nice list on Wikipedia for like all the sister, I would say Fourier based transform. It was nice to look at it. A lot of people have spent a lot of time in thinking of all these different transforms, and they have like very strong mathematical properties. We are not going to redo the signal processing part. I'll just take some time to quickly give you intuition of what these are doing, and will refer you to like more signal processing literature if you want to learn more. So I want to say upfront that this is going to be a hand-wavy discussion of DCT. DCT is actually a very, or like all of these transforms are actually have very nice mathematical properties. You can study them very rigorously, and there are courses, whole courses which do that. So I'll encourage you guys to take them if you like. But these are the basic ideas which are really important for the compression when it comes to these transforms. Okay, point one is most of these transforms are based on the idea of the orthogonal or orthonormal basis, which we have looked at. So we are still working with the same idea. Many of them will exploit the sparsity of signal in some basis. By some basis, I mean some transformation, right? So for example, you'll see that DCT exploits the sparsity of the signal in cosine basis. What that means is if you have some input symbols x, you apply DCT to it, you get this DCT frequency components. If it's a natural signal, most likely you will see that you'll try to have sparse transform components. So you'll have transform components which are already zero. So that sort of allows you to throw them away. So they will have very low energy, right? So that fits very well with what we want to do. They give you the energy compaction property. And the main idea why these work, so obviously, okay, like Nasser said, okay, DCT was also a good approximation to KLT under certain settings. We won't really talk about that here. But one key takeaway why these things works is because of the natural signal statistics. What that means is that if you look at a natural image, a natural audio, right, like whatever image I'm seeing here, a natural video, and then you do some frequency transform of it and you try to see, okay, what are the frequency components, you will see that most of the energy of these symbols will lie at lower frequency compared to higher frequency, right? So you have this natural content which basically doesn't have a lot of energy in the higher frequency components, and then using one of these transforms, you can exploit that essentially. Okay, so this is really one of the key ideas why this constant transform works. It works because your signal itself has statistics and you can use this transform to extract that property that, okay, it is sparse in higher frequency components. So when I transform it, I'll get lower values of these transform components. Okay. This is really, I would say, like, in some sense, one key intuitive jump. It wasn't obvious. You need to know that your world around you is sort of low pass filtered, so as to say. Okay. And actually, it's just not this. So this kind of gives you the Gaussian water filling kind of intuition of why these transforms work. But in reality, like a lot of these compressors, like when you actually see how they throw away the bits for different components or how they assign bits for the different components, it's not just based on energy, it's also based on who is consuming the final lossy compressed signal, right? So for example, images or audio, these are to be consumed by humans at the end of the day. And we as humans also don't really see high frequency signal. So if you have like a lot of high frequency signal in an image, so if you have a lot of noise, you just do a low pass filter of it, you won't even see that noise if it's extremely high frequency. Similarly with audio, like our frequency range at which we hear is set 20 hertz to 20 kilohertz, but in reality very few humans actually go that wide. But for this discussion, let's say 20 hertz to 20 kilohertz. So if you have a signal and it has a lot of bits or a lot of components which when you do frequency transform above 20 kilohertz, you don't need to store it. Like no human is ever going to hear it. And so far we are not compressing, I guess, audio for dogs and animals. So we should be okay. It's for us. So that again gives you a motivation. Even if you have some non-zero, let's say, energy in components above, let's say, 20 kilohertz, you don't want to keep it. You will throw it because it doesn't matter in practice. Your distortion really, the key idea there is, the key switch which happens is your distortion, mean square error is not the right metric. At the end of the day, like, in some sense, mean human error is the right metric there. Right? And we are not going to talk about this today at all. There's actually, in fact, a whole lecture dedicated on this aspects because this is not typically covered in a compression. But it's very important for compression, but it's typically not covered in like information theory kind of classes. So we'll talk more about it after Thanksgiving. But yeah, there are really two reasons working out. So one is more on the KLT side, but the other is on the human side. And if you don't remember anything else, like, this is the key takeaway, like, compress the high frequency components more. You're gonna be fine. And so DCT actually is one of the, again, like I said, most popular transforms in terms of compression. In compression world, it's really popular. But again, like, depending on your application, you might hear about DFT, many other transforms. What DCT is, and we'll look at some examples just right now. Let me just give some summary if you have never heard about DCT before. It's basically discrete cosine transform, right? So it's basically values of cosine function at discrete points. It's just basically that. Again, it's linear. In fact, it is orthonormal. And again, like, it's just a variant of DFT. So you can think of the outputs of DCT as again doing some frequency analysis. So you're just breaking down your signal into different independent frequency channels. It's a real valued transform. So this is where it's actually different from the Fourier transform. Like, FFT can lead to imaginary values, but we don't want our transform components to lead into imaginary values, really. And so, yeah, so this is just like another property of DCT which helps us. And finally, it's a lossless transform. So again, like, we have the TT inverse property working for us. So we can just plug and play. And then various versions of DCT exist. So if you actually go look at the literature, you'll hear something about DCT1, DCT2, DCT3, DCT4. It's okay. All of these are like very, like, they basically differ in the boundary conditions of how these matrices are derived. Yeah, don't worry about it from the compression angle. We'll just think of DCT2, which is like the most. So DCT2 is mostly what's used in many of the practicals, compressors and scenarios. So, yeah. So again, let's build some intuition for DCT2. And again, this is there in the transform coding. Oh, it's reloading. This is again in the transform coding notebook. So you can go home and look at it. We'll put it up on the website. Okay. So I've been hand wavy. I never really defined DCT. I don't think that's the point of this class again, but I have put it here, what your DCT transforms look like. So if you want to go at home and look at it, please do. This will revise your signal processing. So let's start and let's first look at the DCT transform matrix. So again, you have to start with some block size. I can do this. Interesting. Okay. So you have to decide some block size, right, over which you are going to do. So here I have decided 8 as the block size. So my DCT transform matrix is going to be something like 8 by 8. So I just literally wrote down those formulae for the DCT transform, and I used that to generate this 8 by 8 matrix. And the value in each of them is the value which you are going to multiply with that matrix. So what you see is that, like, the first row is basically constant value. So if you were to multiply this with a vector, the first component of the transform will just be the average, so as to not exactly average, some proportional to the sum of all these components, right? And then as you go down, you see some colors changing, some wiggliness happening. So yellow here is positive, blue is negative. It's almost symmetric. But really, like, as I said, like, if you think of each row of the DCT matrix, that's basically coming by, like, discretizing some cosine waveforms. Okay. So what I'm showing here is, again, so this is row 0. So the first row of our DCT matrix, and that's all some constant value for the 7 different components. Then here, this is row 1. And now you see this is like discretized version of a half of cosine like waveform, something, right? Like the blue points are the actual values which exist in the transform, and so on and so forth. So you can see this is like increasing frequencies. Red is just the continuous cosine curve. It's increasing frequency, and then you are basically taking 8 samples out of it. And that basically defines the 8 rows of DCT. So as you are basically going down in terms of your transform components, you are looking at, in some sense, higher and higher frequency, right? Again, this is going to be a hand wavy thing. You can formalize all of these intuitions and numbers, but this is just to like give you a quick sense of what DCT is. Okay, so now once you have looked at the transform, we can actually use this transform to do the forward transform and the reverse transform. So these are just function which takes some signal. And again, like here I've just spelled it out. There are also SciPy functions, etc., which you can use in practice, but this is for pedagogical reasons, so you can just write down these formally. Nothing fancy. Okay, so now let's look at some of the examples, like what happens when you apply DCT in various different cases. Okay, so the first example is that of a constant signal. So suppose you had a constant signal with constant values. You can look at the DCT, and there you will see that, oh, it peaks at the 0 value, right? And that makes sense because here you only have a constant frequency, nothing else. And then when you take the IDCT of this transform components, DCT, you recover back the original signal in green. Yeah? Everyone's following what's happening here, roughly? Yeah? Okay. Okay, so now in the next example, let me just take some sinusoids with varying frequency. And so this is now my input signal. It has some frequency. I look at its DCT coefficient. It has value 0 for most of the high frequency components, so higher values of my DCT, but it somehow some peaks at the index 2, so like component peaks. And then when you apply the IDCT on this DCT, you recover back the original symbol. And what you see is like on the left, as I go down, I keep increasing the frequency of my signals. And what you see is that the DCT coefficients, now the energy in the DCT coefficients is moving towards right. Right? So it's like, again, your DCT is tracking the frequency of the signals in substance. The higher the value of the DCT component in your transform side, the higher the component which is non-zero in the transform side, that means higher the frequency it has, the input signal has. Okay, so again, it's tracking frequencies is what I want to say. It's not really a delta function because all of this depends on, as soon as you go from continuous to discrete, a lot of things starts depending on the boundary conditions and exact samples. If you know about it, great. If you don't know about it, don't worry about it right now. Okay, so now let's look at another example where we just have a general signal. I just made some triangle-like signal. I did its DCT. So again, it's 8 by 8. So I have 7 transform components. Now for this signal, I see it has more low frequency component, but there is some non-zero high frequency component. For example, this component at 5. You can't see my pencil, right? Okay. So this component at 5, it's not really 0. There is a small stem. So there is some small value, but it's mostly 0 at the higher frequency components. And again, when I do the IDCT of this thing, you get back the same signal. So far, so good. But now you guys know what we are going to do, right? So we are not going to keep the whole DCT when we are doing the lossy compression. We are going to throw away. And the way we are going to throw away is, again, let's just use our intuition. We don't have a theory right now to help us. Let's just use our intuition. What will you do? You'll like throw away the components which have very low power, right? That's like one way to compress. And because then you don't have to worry about a whole stream, essentially, of things to quantize. Correct? And so let's just do that for this particular signal. And so what I'm going to do is, basically I'll have a threshold, and whatever components lie below that threshold, I'm going to just put it to 0. Okay. So the first one is threshold 0. So I basically keep all the components, and you see that the green reconstructed signal is matching exactly. But now I went ahead, I took some very small threshold like 0.25. So everything in this plus minus 0.25 window, I'm going to put it to 0. Actually, just this guy goes to 0. So that was non-zero, here it's 0. You can't even see it. And you get this recovered signal. So green is the reconstructed signal, red is the same original signal. So now you see, like, okay, it won't match exactly, right? Because DCT, IDCT would match exactly only if you have the same components. But now you see, you introduce some small error. Okay, so run the experiment. Let's keep increasing the threshold. 5. Now you see at 0.5, all of my high frequency components have gone to 0. And I'm actually just keeping 3 components instead of 8 components. But still my errors seem like somewhat controlled. It's not really that the green signal looks super different from the less red, right? Obviously, you are introducing distortion, but it's not too much. Then you keep increasing, keep truncating. At some point, you basically keep you keep nothing all the DC signal. At this point, obviously, your errors are just over the roof, right? If you just keep the first component, that's basically saying, oh, I'll just transmit the average of these things. So that's not really useful. But maybe somewhere here at threshold 2 or maybe at threshold 1, where you're keeping just 2 or 3 components, depending on the scenario, these errors might be more manageable, right? And so this is really what DCT does, right? So you're splitting it into transform components and you're throwing away maybe components. So in this example, we completely threw away. But again, like we discussed in the previous example, where rho was 0.5, maybe you don't completely throw away. Maybe you compress some components more versus some other components less, and that's very common in a lot of practical transforms. Okay, and like this notebook is available, so you can go over it. Any questions? Because after this, we're gonna just go 5 more minutes and have some fun. Like we're gonna collect everything which we have learned and make our first lossy compressor. Yeah.
How is it different from Fourier transform?
How is it different? You can think of it as a sister like transform. Basically, the boundary conditions are different. So in Fourier transform, like here you assume symmetricity, and it's basically a different transform, very similar like Fourier transform. But in Fourier transform, unless you have, I think the real reason is it comes from the block conditions, boundary conditions. So when you have these boundary conditions, you want continuous signals. And in Fourier transform, you can show that DCT accommodates the boundary conditions better when you break down in blocks. Maybe I'm not able to express it very clearly. I'll answer it better after the class. You want to?
It's like for constant type signals, I think DCT is more concentrated at lower frequencies than the DFT. It's something
Yeah.
because cosine is like
Flat, yeah.
versus sine sort of sharp,
Yeah.
something like that.
So basically sine has a higher derivative at 0 actually. So in boundary conditions, so what happens is you have this signal, but you are chunking it, right? So for example, in this 8x8, I won't really always get 8 signals, right? I'll have a continuous stream of symbols. I'll chunk 8, then chunk 8, then chunk 8, right? And so what you want is when you do this and get the inverse transform, you want the boundaries shouldn't be like, oh, there's a sudden jump. Imagine you had first block, last element as value 1, and similarly again, a bunch of values 1 in the second block initial component. You want that constant to remain constant across the blocks. And DCT, like again, it's a bit mathematical, like I think I'll explain it, I'll post this on it, a much more detailed answer after the class, but DCT ensures that this constant signal remains constant when you throw away compared to DFT, which can lead to huge shifts. And so you can imagine if you have huge shifts and you have some continuous signal, that might be very odd to see even in lossy compression. That shows that's a very common artifact called blocking artifacts because you see things messing up at the boundaries. Let's maybe go a little ahead and I'll post much more detail. But for now, if you don't know anything, you can think of it as a sister transform of DFT. Okay. So I'll just go 5 more minutes. I do want to do this. This is really the pipeline for our bare bones practical lossy compression at this point, right? So we start with some symbols xn. You do some transform, you get yn, you quantize this, you get some codebook vectors. After that, you have to do entropy coding, right? So you do lossless coding of these codebook vectors, whatever you get. That gives you the bit stream. At the end of the day, you have to get to the bit stream. And this determines the rate. And then on the decoder side, you first do exact reverse steps, right? So you first do entropy decoding. That gives you the codebook indices, which you can use to dequantize, which gives you some recovered transformed vectors. And finally, you do the inverse transform to get back your original signal. And your distortion is between what you started with and what you ended with, right? So this is like the rate distortion trade-off. And the key point to note is the only lossy step here is quantize. Right? And this is really, like, I would say, this is like the bare bones practical. At this point, you already have, if you do all these steps, you have a practical lossy compressor. In fact, what we will see in next lecture, JPEG essentially does this, and it really optimizes each block to its fullest. But it's essentially this exact block diagram at its core. Okay, and so we have lots of design decisions, like you can choose different transforms, you can choose different quantization, you can choose different entropy coding schemes, and we have given you some of these in the class, right? But again, something to note, there are many other options which we might not have covered, but so we have already covered like some options for each of this. So let's just go ahead and look at one. So we're gonna go and look ahead at an audio compressor, which basically does this exact same thing. And this thanks to Shubham for having this notebook. So our audio compressor is going to do exactly these steps which we talked about, sorry. So we are gonna do transform, in our case DCT. We are gonna quantize using just a scalar quantizer. And then we are gonna do, we are actually not gonna do entropy coding, but we're gonna look at it. Okay. So let's just look at this notebook. Okay, so this is just like setting up some basic code. You want to be able to quantize and quantize. You will do DCTI, DCT. You will do something like low pass DCT, which is exactly the thing which we looked at. In some sense, like thresholding the components and keeping the others to 0. And then there are a bunch of other helper functions. And so in a simple audio compressor, you can actually play with 2 components, right? You can play with the frequency cutoff, which is like saying, okay, how many components do I actually keep? Or you can play with the number of quantization levels, and those will have like different effects. So this notebook has lots of quiz questions, so go again, do attempt them. So let's just start. So I have already loaded the data here. And so what you see here is the transformation for one of the file. On the x-axis is like the frequency component, so you can think of these as independent transform channels. And on the y-axis is the energy. And if you see, for this natural signal, there is a natural cliff. Maybe I should be able to zoom out. Okay, I'm not able to zoom this out, but yeah. So you can see that like for this whatever audio signal, your energy suddenly drops from this point onward. So this was the point where natural signals automatically have their statistics such that there is low energy at higher frequency. Yeah. And so we can do 2 things. We can either throw away, we'll decide to throw away all the components above a frequency, or we can decide to discretize each component with more or less number of codebook vectors, right? So, okay, let's just hear this out. I don't know if this will work. Let's see. Okay. So this is the original audio, and again, if you've done homework 3, you know one of the instructors is probably Pokemon fan, so you can guess later. But okay, you can hear the whole thing. So this is just the original audio. I wanna be the very. Okay, and so first let's look at what the low frequency cutoff version of this audio looks like. I think the audio is coming from here. Okay, so you observe that, okay, it still was like the Ash wants to be the very best, but was somehow very dull about it, right? Like we removed the high frequency components, it sounded very dull. Okay, so that's one way to do lossy compression. But I could also just reduce the number of quantization levels, keep all the frequencies. Let's do that next. I wanna be the very best. Okay, so in this case, you can hear like all the instruments and the high frequency stuff, the treble, the bass, but there was like a very static noise behind, right? Like there was like, let's just hear it quickly. No one ever was. It's like kind of going on, right? So that's basically being introduced because now you have increased the quantization level. So you see how playing with these 2 different knobs led to different distortion in some sense, right? Like very different sounding distortion. But what you can do is like you can go ahead and plot it as the rate distortion curves, which we have looked at before, right? So on the x-axis is rate, y-axis is distortion, and we are doing many different colors at different frequency cutoffs, different symbols are different quantization level, okay? And this is what people also do in practice. You would actually, like this is what I was saying, if you're a streaming service, you will actually encode this Pokemon in various of these forms. And you will basically keep the points which give you the lowest distortion at any given rate. So what you will see here is at low bit rate, you can't see whatever I'm drawing there, okay. So at low bit rate, you have colors which are changing, right? Whereas at high bit rates, like the things, so this black dot is the Pareto-optimal black line, you see the number of quantization levels are changing, the symbols are changing. So what's really happening is that at extremely low rate, you are benefiting by including more and more frequencies. But after a point, it doesn't really matter to include that more frequency because that anyways has low energy. You can just throw it away. Rather, really keep the frequencies which are low in much, much higher fidelity, right? So this is like this. Every streaming service has this. These are called like encoding tables, and you will have some version of this. People playing with these knobs in practice to figure out like what's the optimal way to compress my symbol. Okay, and so this was like we did some transform and then quantized. But let's say your friend who never took this class actually didn't transform. He directly quantized, right? So this is similar to the example which we looked above. In that case, basically, you get these black dots, which are much higher in distortion. So now you can see for basically similar power of quantization, you get much higher distortion compared to if you were doing transform coding. I think there was an example. Okay, maybe I missed this, sorry. So this, yeah. Okay, yeah, so, yeah, I think this is an example, let's just hear it. Sorry? Yeah.
That's the low pass and the
Yeah.
one below is the direct.
Exactly. So this is again the low pass one, so with transform and quantize, and the next one is just direct quantized.
I wanna be.
Okay. And this is the second one.
I wanna be the very best.
Okay. So here I tricked you because both of these symbols basically have the same MSE. So they roughly sounded similar. But if you look at the bit rate, the direct quantization one took 160 kbps. So it's here, took 160 kbps, whereas transform plus quantize one took just 86. So similar sounding, but transform clearly helps. And just the last thing which I want to show, and I'll end the lecture here is, okay, this was a bare bones lossy compressor. It was literally that pipeline. We did DCT, we did some quantization and we worked around. But there is a very popular compressor, MP3. So we might want to compare how our compressor performs with respect to MP3.